Hello friend, welcome to this lecture. In this lecture we will discuss the parabolic equation. In particular we will discuss heat equation as a prototype of parabolic equation. So, here if you recall we classify our partial differential equation say uxx auxx plus buxy plus cuyy, because classification is done only say linear second order terms. So, here if b square minus 4 ac is equal to 0, we call these kind of equations as a parabolic equation. So, we will discuss this equation ut equal to c square uxx or say some constant times uxx, and we say that here if we look at a is your constant c square and b is 0 because there is no mixed partial derivative is present, and c is also 0 because we do not have double derivative corresponding to yy or other variable. So, here we can say that b square minus 4 ac is coming out to be 0. So, we can say that this heat equation, which is written as ut equal to some constant times uxx, is a parabolic equation. And now we are looking at how to solve the heat equation and the other properties of heat equation. So, first let us consider the heat conduction problem in an infinite rod with the following assumptions. So, here we consider an infinite rod, and this is going to say. So, here we consider that the rod is homogeneous and the position of the rod coincide with the x axis. So, we will say that this rod is kept along with the x axis, and rod is sufficiently thin so that the heat is uniformly distributed over its cross section at the time t. So, first thing is that rod is homogeneous and position is coincide with the x axis. Second thing is it is sufficiently thin so that heat is uniformly distributed over its cross section at the time t, and third is the surface of the rod is insulated to prevent any loss of heat through the boundary. And let us say that this heat distribution is represented by uxt. So, this uxt represent the heat in the rod at point x and at time t. So, uxt represent the temperature in the rod at the point x at time t. Now, what we are considering a problem of heat conduction in an infinite rod, which is equal to ut equal to k uxx minus infinity, where x lying between minus infinity to infinity and t is greater than 0, with the initial condition that ux0 equal to f of x and x lying between minus infinity to infinity. So, here this constant k is a constant which depend on the material of the rod, and here this represent ux0 equal to fx represent that at time t equal to 0 the temperature at the point x is given by f of x. Now, we want to find out using the equation 1 and 2 to find out the temperature at any point at time t. So, suppose the Fourier transformation of uxt with respect to space variable is given as u alpha t. So, here we are solving this one dimension heat problem with the help of Fourier transform. So, here since we have two variable u x and t, so here we apply the Fourier transform with respect to the space variable, that is x here. So, here we simply say that, let us say that uxt take the Fourier transform of uxt with respect to the variable x, and let us it is denoted as u alpha t. It means that Fourier transform of uxt, which is denoted as u alpha t, is equal to 1 upon root 2 pi minus infinity to infinity uxt e to power I alpha x dx. So, here we are taking the Fourier transform with respect to the space variable, that is x here. So, and u alpha t is denoted by this thing. So, now using the Fourier transform, let us transform our equation 1 in a frequency domain. It means that apply Fourier transform on this ut equal to k uxx. So, here we have if you take ut equal to k uxx, and if we apply the Fourier transform, it is 1 upon root 2 pi, and here it is minus infinity to infinity dou u by dou t e to the power I alpha x dx equal to k times 1 upon root 2 pi minus infinity to infinity and u xx and e to the power I alpha x dx. Now here since this is integration is with respect to t, so I can write this as d by dt of the whole thing, that is 1 upon root 2 pi, 1 upon root 2 pi you can cancel it out. So we have say minus infinity to infinity u e to the power I alpha x d of x equal to k times, here it is minus infinity to infinity and u x x e to the power I alpha x d of x here. So this I can write it as u alpha t. So we have written that it is d by dt of u alpha t. So we can write this as ut. Now we have to handle this term. It means that we have to find out the Fourier transform of uxx. So how to find out the Fourier transform of uxx? It is what, minus infinity to infinity uxx e to the power I alpha x dx here. So here we apply the integration by part and we transform the derivative on e to the power I alpha x. So we write first integration of second, that is ux between minus infinity to infinity minus infinity to infinity integration of this and e to the power I alpha x derivative of this. So I alpha will come out d of x. Now here if you look at the boundary conditions, boundary condition is what, that here as x tending to infinity we assume that the derivative ux is tending to 0. So it means that here ux is tending to 0 as x tending to mod of x tending to infinity. So using this boundary condition, that at infinite length the temperature distribution is going to be 0. So not only ux we are assuming that u is also tending to 0 as mod of x is tending to infinity. So these are the physical condition we are applying on this infinite rod case. So using these physical condition, this part is simply gone. So this I can write it minus I alpha minus infinity to infinity ux e to the power I alpha x dx. Now still we have to apply one more time, and when you apply we have minus I alpha, and when you write it here it is first integration of second. So e to the power I alpha x u minus infinity to infinity minus again will come a minus I alpha minus infinity to infinity u and e to the power I alpha x dx. Now here again we use the same thing, that u is tending to 0 as mod of x tending to infinity. So this will simply move, and what you will have, it is minus I alpha whole square minus infinity to infinity u e to the power I alpha x dx, and which is nothing but your u alpha t here. So I can write this as minus I alpha square u alpha t. So this is what, this is your minus alpha square u alpha t, right, and k is already there. So we can write that it is k alpha square u. So we can write it here. I think there is some problem here. Yeah, it is minus alpha square u alpha t, that is what it is written, and using k you transform here and you will have ut plus k alpha square u equal to 0. Here u is your u alpha t here, and if you look at this is a differential equation in terms of variable t here. So here this is an ordinary differential equation given in terms of t, and we know this is first order and we can easily solve, and our solution is given by u alpha t equal to a alpha e to the power minus alpha square k t. Now here this a alpha is an integration constant which is constant with respect to the variable x, and we can determine from the initial condition as follows, because the constant we can find out using the initial condition. And what is the initial condition? That ux0 equal to f of x. But since this equation is given in terms of frequency domain, or we can say that in alpha domain, so we transform our initial condition also in frequency domain. So let us write down u alpha 0 as Fourier transform of ux0, that is 1 upon root 2 pi minus infinity to infinity ux0 e to the power I alpha x dx. Now let us denote this quantity as f of alpha. So we are writing 1 upon root 2 pi minus infinity to infinity ux0 is f of x e to the power I alpha x dx. Now let us denote this as f of alpha. So it means that Fourier transform of f of x is given by f of alpha. So, using this initial condition, what is your here u alpha t equal to a alpha e to power minus alpha square k t. Now, put t equal to 0, then your u alpha 0 is coming out to be f of alpha. So, we can write this is f of alpha equal to a alpha and this is 1. So, a alpha is coming out to be f of alpha, and so we can write u alpha t as f of alpha into e to power minus alpha square k t. So, now we have solved our problem in frequency domain, but we want our solution in x and t domain. So, we can find out our u x t by taking the inverse Fourier transform of u alpha t. So, let us take the inverse Fourier transform of u alpha t, and if you look at here, it is I can write this as a Fourier transform of f of alpha into e to power minus alpha square k t. So, if I say that this is e to power minus alpha square k t is a Fourier transform of some function, say g of x, then I can write this u alpha t as what? It is f alpha into g of alpha. So, here we can use our convolution theorem to write down our solution u x t as f convolution f inverse Fourier transform of e to power minus alpha square k t. So, and what is this convolution means? Here we define convolution like this: f convolution g is equal to 1 upon root 2 pi minus infinity to infinity f of u g of x minus u d of u. So, here this convolution is defined like this. Now, to write down this solution properly, I need to find out the inverse Fourier transform of e to power minus alpha square k t. So, for that we define g of x as inverse Fourier transform of e to power minus alpha square k t. So, this I can write it as 1 upon root 2 pi minus infinity to infinity e to power minus alpha square k t e to power minus I alpha x d alpha, and we can simplify this expression, and we can say that it is coming out to be 1 upon root 2 pi times this quantity is coming out to be root pi upon root k t e to power minus x square upon 4 k t. And how we can find out? Let us write down here, and let me write it here minus infinity to infinity. I can write e to power minus k t out, then we have alpha square, and then we have plus, and we have what? We have taken alpha out. So, it is I alpha x divided by k t here. So, we can write it like this and d alpha. So, to solve this, let us make the perfect square here. So, we can write here that since I can write this as I x 2k. So, I can write this as alpha square plus 2 times alpha I x upon 2 k t, right. So, if I want to make a perfect square, I need to add something, I need to subtract something. So, I am adding this I x upon 2 k t whole square, and similarly I am subtracting I x upon 2 k t whole square, right. So, this I can write it like alpha square plus 2 alpha I x upon 2 k t plus I x upon 2 k t whole square minus I x upon 2 k t whole square d alpha. So, I can write this as minus infinity to infinity e to power minus k t. Now, this part I am writing as alpha plus I x upon 2 k t whole square, and what is left here? It is e to power this minus and minus plus, it is and then I square will come out. So, it is minus x square upon k t, and 1 k t will cancel out. So, we have 4 k t d alpha. Now, since this integration is with respect to d alpha, so I can write this as e to power minus x square upon 4 k t into minus infinity to infinity e to power minus here we have k t, and this is alpha plus I x upon 2 k t whole square and d alpha. So, let us make this quantity like k t alpha plus I x upon 2 k t as some beta. So, by assuming this, and in fact root of this, then what you will get? Then root of k t d alpha equal to d beta, and if you look at the limit is coming out to be minus. So, this whole thing I can write it e to power minus x square upon 4 k t, limit will be as it is, and here what you will get? E to power minus beta square and d beta divided by root k t, this quantity will come down, and we already know that minus infinity to infinity e to power minus beta square d beta is your root pi. So, I can write this as root pi, and this root kt will be here into e to power minus x square upon 4 kt, and that is what we have written here. So, it means that this quantity minus infinity to infinity e to power minus alpha square kt into e to power minus I alpha x d alpha, and if you solve this, we have this quantity, that is root pi upon root kt e to power minus x square upon 4 kt. Now, by simplifying, we can write it as 1 upon under root 2 kt e to power minus x square upon 4 kt. So, our gx is coming out to be this quantity. Now, our solution is what? F convolution gx. Now, f using the formula that f convolution g is given as 1 upon root 2 pi minus infinity to infinity f u g of x minus u d of u. So, here we can write this as 1 upon root 2 pi, and here we have one under root 2 pi here and one root 2 kt here. So, 2 can be taken out, and we can write 1 upon 2 root pi kt minus infinity to infinity f of xi exponential of minus, in place of x I am writing here, we are writing x minus u. So, here u is replaced by xi. So, I can write minus x minus xi whole square upon 4 kt d xi. So, here we simply say that this is what we can simply write f convolution gx as 1 upon root 2 pi minus infinity to infinity f xi. Now, in place of in argument of g, we write x minus xi d xi. So, we already have g of x. So, we can define g of x minus xi, and we have written like this. So, our solution u x t is given as 1 upon root 1 upon 2 root pi kt minus infinity to infinity f xi exponential of minus x minus xi whole square upon 4 kt d xi. So, it means that this is our solution, and once we know our initial condition, then we can find out our temperature distribution at point x at time t by this formula. Now, let us say that we consider a particular example in which your f xi is given by this, the initial temperature is given by f of x equal to 0 when x is less than 0, and a constant value a which when x is greater than 0, and here we are assuming for simplicity that our k is equal to 1 here. Then our simplified solution is given by u x t as a upon 2 root pi t 0 to infinity exponential of minus x minus xi whole square upon 4 t d xi. Now, here if we put this term x minus xi upon 2 root t as say eta, then we can simplify our u x t as follows, that you can write a upon root pi minus x upon 2 root t infinity e to power minus eta square theta, which we can simplify this integration range of integration, we can write it minus x upon 2 root 2 to 0 plus 0 to infinity e to power minus eta square theta. So, this quantity is coming out to be root pi by 2. So, here we can using this value this term can be written as a upon 2 plus a upon root pi 0 to x by 2 root t e to power minus eta square theta. Now, this expression is given as error function of x upon 2 root t. Here error function of y is written as 0 to y e to power minus eta square d of eta. So, using the expression for error function, we can write down our u x t is given as a by 2 1 plus error function of x upon 2 root t. So, here it is a very a particular case when we assume that k is equal to 1 and f x is taking this value. So, this is a very particular example of this, but in general if f is given some value, then our solution u x t is written as 1 upon 2 root pi k t minus infinity to infinity f xi exponential of minus of x minus xi whole square upon 4 k t d xi. So, this is the solution. Now, we will move to semi infinite domain. So, it means that here your length is only infinite semi infinite, and one end is kept at say at 0 temperature. So, we look at our problem like this, that find the temperature distribution in the semi infinite medium x greater than equal to 0 when the end x equal to 0 is maintained at 0 temperature and the initial temperature distribution is given as f of x. So, problem is what, that w by w t equal to k w u by w x square, x is between 0 to infinity, t is greater than 0. Boundary condition is that the point x equal to 0 is kept at 0 temperature, that is u0 t is equal to 0, and initial condition is that ux0 is equal to f of x when x is lying between 0 to infinity. And here, as we have assumed before, that our temperature and its derivative corresponding to x both tend to 0 as x tending to infinity. So, this is the whenever we consider any infinite, semi infinite say problem, we always assume these kind of condition that u and its partial derivatives are say tending to 0 as mod of x tending to infinity. So, here since we are considering only the positive side, so it means that x as x tending to infinity, u and derivative u by derivative x both are tending to 0. So, here I cannot apply the Fourier full Fourier transform. So, here we will apply say Fourier transform defined for only between 0 to infinity. So, we have two choices, one is Fourier sine transform and another one is Fourier cosine transform. And so, which Fourier sine transform we should apply or Fourier cosine transform we should apply, that is our question. So, let us handle some result and say that based on that result we can identify that based on the initial condition and boundary condition we can define that whether we should apply Fourier cosine transform or Fourier sine transform. So, here let us look at the following remark, that in the case of semi infinite domain we find the solution using Fourier sine and Fourier cosine transform, and in this regard we have the following result, because if you look at this term can be handled very easy, that it is d by dt of u alpha t, and but we have to handle this term by integration by parts. So, we have to handle when we do integration by part, then we have a boundary term, that is say what happened when we have what is the value of u or ux at the end point, lower end point, that is x equal to 0. So, here because we have only this condition that u derivative u by derivative x both tend to 0 as x tending to infinity, but we do not know the behavior of u and ux at the end point x equal to 0. So, depending on this we will choose Fourier cosine transform or Fourier sine transform. So, let us first consider the result, that Fourier sine transform of derivative u by derivative x square with respect to the space variable x is given as root 2 by pi alpha u x t given at x equal to 0 minus alpha square Fourier transform of u x t, and Fourier cosine transform of derivative u by derivative x square is given as minus root 2 upon pi derivative u by derivative x given at x equal to 0 minus alpha square f c Fourier cosine transform of u x t. This simply represent that we are finding the Fourier sine transform of u x t with respect to the variable x, and this represent that we are finding the Fourier cosine transform of u with respect to the variable x, and we are considering the alpha as the frequency domain here. So, here if you look at these two formula, then if we apply, if you look at if we apply Fourier sine transform, then I need the value of u at x equal to 0, but if we apply Fourier cosine transform, then I need the value of derivative u by derivative x at the point x equal to 0. So, this will give you the idea that I should apply Fourier sine transform or Fourier cosine transform. For example, we have this result that u x 0 equal to f of x. So, here the point at x equal to 0, yeah, here we condition u0 t equal to 0 is given. So, here this will give you that here we should apply the Fourier sine transform, because in Fourier sine transform only we need u at x equal to 0 n, but if we apply Fourier cosine transform, then I need to have the value of derivative u by derivative x at x equal to 0, which is not given here. So, in this particular example, since boundary condition is given in terms of u, we will apply Fourier sine transform, and if this boundary condition is given in terms of ux, then we will apply Fourier cosine transform. So, first let us have a simpler proof of these two results. So, let us look at the first result. First result is that Fourier sine transform of derivative u by derivative x square is given as root 2 upon pi 0 to infinity sin alpha x derivative u by derivative x square dx, and then we apply say integration by part. So, we write first sin alpha x into integration of this derivative u by derivative x square, that is derivative u by derivative x between 0 to infinity minus root 2 pi upon pi alpha, derivative of this sin alpha x, that is cos alpha x into alpha, and integration of derivative u by derivative x square, that is derivative u by derivative x. Now here we already assume that this derivative u by derivative x is tending to 0 as x tending to infinity. So this at point infinity, as x tending to infinity, this point is gone. Now at point at x equal to 0, since sin of 0 is 0, so this boundary point boundary values will be cancelled out. So we then the right hand side of the above equation is now reduced to minus root of minus square root of 2 upon pi alpha 0 to infinity cos alpha x derivative u by derivative x dx. Now again we apply integration by part, and we can write minus root 2 upon pi alpha into in a bracket we are looking at the expression for this. So here it is what this cos alpha x integration of derivative u by derivative x, that is u x t, plus alpha 0 to infinity differentiation of cos alpha x, that is minus sin alpha x will be there. So minus it will come out to be plus, and u x t integration of derivative u by derivative x, and this is what this is basically the Fourier sine transform of u x t. So and again since we have assumed that u is tending to 0 as x tending to infinity, so at this point your this point is gone to be 0. So only thing remain at x equal to 0 u x t cos of alpha x value. So here this boundary value at x equal to 0 is now given by this. So we can simply say that it is under root 2 upon pi alpha u x t at x equal to 0 minus alpha square Fourier sine transform of u x t. So we can say that using this value I can write Fourier sine transform of derivative u by derivative x square is equal to under root 2 by pi alpha u x t at x equal to 0 minus alpha square Fourier sine transform of u x t. And in a similar way we can prove the second result, that if we take u x t equal to 0, u x t tending to 0 and derivative u by derivative x is tending to 0 as x tending to infinity, we can write Fourier cosine transform of derivative u by derivative x square is equal to minus root 2 upon pi derivative u by derivative x defined at x equal to 0 minus alpha square Fourier cosine transform of u x t at x tending to alpha. So therefore if we summarize this, in case of semi infinite domain problem, the choice of sine or cosine transform will depend in the form of the boundary condition at the lower limit of the variable which we want to exclude. Here our problem point is derivative u by derivative x square, how to handle this. So this we want to exclude. So here we want to see the availability of u and ux at the lower end point. So here thus to handle the term derivative u by derivative x square in PD, we require that if u is given at x equal to 0, then we apply Fourier sine transform, and if derivative u by derivative x at x equal to 0 is given, then we apply Fourier cosine transform. So in using this observation in our problem we will apply Fourier sine transform. Here we apply Fourier sine transform because boundary condition is given in terms of u at x equal to 0. So applying Fourier sine transform we have this. So taking the Fourier sine transform of the equation 6, we get under root 2 by pi 0 to infinity derivative u by derivative t sin alpha x dx equal to root 2 upon pi k times 0 to infinity derivative u by derivative x square sin alpha x dx. Now we have this value available for us, and we can write dus by dt, where us we are given as root 2 upon pi 0 to infinity, so u x t and sin of alpha x dx. So we are denoting us as this value. So we can write this as du by dt equal to k times, and here we have using our result 1, we have alpha u 0 t minus alpha square us, but our u 0 t is coming out to be 0. It is already assumed that we have a homogeneous boundary condition. So this part is gone, and we can write this as du by ds minus plus k alpha square us equal to 0. So our using the boundary condition we obtain that we have du by dt plus k alpha square us equal to 0, and now we can find out this k by using the initial condition 8, that is us equal to f of s alpha at t equal to 0 here. So, here our equation is du by dt equal to k times this quantity. Now, this boundary condition is already given as u0 t is equal to 0. So, using the boundary condition we obtain du by dus upon dt plus k alpha square us equal to 0, and we also given a initial condition. So, applying Fourier sine transform of the initial condition, we can write us equal to fs alpha at t equal to 0. So, this is the initial condition is given to us. So, we have ordinary differential equation 11 along with the initial condition 12, that us at t equal to 0 is given as f of s alpha. Now, we can solve this equation number 11. I can write this equation 11 as d by dt of us e to power k alpha square t equal to 0, and this can be simply solved by writing us k e to power k alpha square t equal to constant. And how to find out the constant? There we can use the initial condition that us at t equal to 0 is given as f of s alpha. So, using this we can write that your constant value is coming out to be fs alpha. So, we can write us e to power k alpha square t equal to fs alpha, and we can write thus our solution is given as us equal to fs alpha e to power k alpha square t. So, this is the Fourier sine transform of uxt. So, once we know our Fourier sine transform in of uxt, then we can find out uxt by taking the inverse Fourier sine transform of this equation. So, uxt we can write under root 2 upon pi 0 to infinity fs alpha e to power minus k alpha square t into sin alpha x d alpha. So, by solving this we can find out the solution in terms of x and t. So, we can write our solution as uxt equal to under root 2 by pi 0 to infinity fs alpha e to power minus k alpha square t sin alpha x d alpha. So, here we found the solution of semi-infinite region when the initial condition is given in terms of boundary condition is given in terms of u. Now, consider another problem of the same semi-infinite domain, but this time your boundary condition is given in terms of ux. So, here problem is what? Find the temperature distribution uxt in semi-infinite rod lying x between 0 to infinity, determined by the following PD, that is ut equal to k uxx, where x is lying between 0 to infinity, t is greater than 0, subject to the initial condition that ux0 equal to f of x, and the boundary condition is given that ux0t is equal to minus of u0 when x is greater than 0 and t greater than 0. And here again we have the same physical condition that u and w by x both tend to 0 as extending to infinity. Now, if you look at the boundary condition, boundary condition is given in terms of u of x. So, we apply Fourier cosine transform to handle this problem. So, applying, since w by x is given at the lower limit, we take the Fourier cosine series transform of the given PD to obtain the following equation under root 2 by pi 0 to infinity w by t cos alpha x dx equal to k times under root 2 by pi 0 to infinity w by x square cos alpha x dx. Now, we already have the either we use the our result 2, or we can simplify this by taking say applying integration by part, and we can write k upon root 2 by pi w by x cos alpha x 0 to infinity plus k alpha under root 2 by pi 0 to infinity w by x sin alpha x dx. So, here we applied integration by part, and we can write it like this. Now, we already know that w by x tend to 0 as extending to infinity. So, at this point at this boundary point we have this value 0, and we have only term left corresponding to x equal to 0. So, we can write minus k times under root 2 by pi w by x at x equal to 0 plus k alpha. Again we simplify this problem using integration by part. We can write k alpha under root 2 by pi u sin alpha x at 0 to infinity minus k alpha square under root 2 by pi 0 to infinity u cos alpha x dx. Now, here if you look at this boundary point, so x at x tending to infinity, u is tending to 0. So, this part is gone, and at x equal to 0, this sin alpha x is 0. So, this boundary condition will be vanished. So, what we have d by dt of uc is equal to minus k upon root 2 by pi w by dou x at x equal to 0, and this value is given as minus of u naught. So, minus minus will give you plus. So, we have under root 2 by pi k of u naught, and this quantity is what? This quantity is given as Fourier cosine transform of u x t. So, we can write this as minus k alpha square Fourier cosine transform of u x t, that is u c. So, here we have d by dt u c equal to root 2 upon pi k u naught minus k alpha square u c. So, here we have a simple ordinary differential equation, non-homogeneous ordinary differential equation in terms of u c, and we can simplify this by writing d by dt of e to power k alpha square t u t equal to under root 2 by pi k u naught e to power k alpha square t. Since we can find out the integration factor by e to power k alpha square t, we multiply and we can write it like this, and then we simply integrate, and our this equation is now reduced to this, that e to power k alpha square t u c equal to root 2 upon pi k u naught integration of e to power k alpha square t dt plus some constant, integration constant we have to apply. Now, to handle this integration constant, we take the we look at the initial condition and take the Fourier cosine transform of the initial condition, and we have u c equal to f of c when t equal to 0. So, using this condition we can find out our constant, and it is coming out to be that constant is given as this is given as f of c. So, this is f of c equal to under root 2 by pi k u naught, and integration of this will be e to power k alpha square t divided by k alpha square. So, we can write it here under root 2 by pi u naught upon alpha square plus constant. So, we can find out the value of constant and we can put it back. So, we have e to power k alpha square u t u c minus f of c equal to under root 2 by pi u naught upon alpha square e to power k alpha square t minus 1, and we can simplify and we can write u c as under root 2 by pi u naught upon alpha square into 1 minus e to power minus k alpha square t plus f of c e to power minus k alpha square t, and we can find out our solution u x t by taking inverse Fourier transform of the expression given in terms of equation number 19, and our solution is given as u x t equal to under root 2 upon pi 0 to infinity cos alpha x u c t d alpha. So, by putting the expression for u c t, we can find out the solution for this semi infinite region when boundary condition is given in terms of u x. So, that is all for this lecture. So, in this lecture what we have considered, we have considered the heat equation in infinite region and in semi infinite region when we have two different kind of boundary condition is given. If boundary condition is given in terms of u, we will apply Fourier sine transform, and if boundary condition is given in terms of u x, then we we solve our problem by applying Fourier cosine transform. So, with this I end our lecture, and in next lecture we will continue our discussion of solution of heat equation and finite domain and etc. Thank you for listening us. Thank you.